Greetings, everyone. Let's continue with our arithmetic. And the title of this section is called, it's a bit of a hodgepodge of stuff, but one of the main things that we'll do is so-called solving congruences. What is congruence? That is refers to this mod. That, in other words, we will work within, so remember if, let's say, you work with 75, so mod 75, working mod 75 means that you work in this collection of numbers that are the remainders of division by 75, so this goes up from, it goes from 0 all the way to 74. So working modulo 75, that is working with these numbers, and therefore all the results should be within those numbers. And that's, instead of calling this equations, we call this congruences. I want to give you an example. So let's suppose we have this equation, 4x is equal to 7. Let me do this in red, perhaps, because I want to warn you what, I want to just review how do we solve linear equations. That's very old stuff, and what you do is you say, okay, divide both sides by 4, and then you find x is 7 over 4, right? But that is where you're working now. What is this result? This is a rational number. So you're working in what we now denote by q. These are the rational numbers. That is not this guy. So how do we work in this guy? How do we solve this equation? So the original equation was this one, right? How do we, I'll write it now in black because now I'm going to do it correctly. How do we solve this equation? 4x is 7, but in 75, which remember we will write this way. So how do we solve this equation? Can we divide by 4? Can we do the same trick? And essentially, yes, but 1/4 is, the problem is, so problem, 1/4 is a rational number, right? And 1/4 is in there. And that's not in is in this one, but not in here. So it's in Q, but not in Z5. So it's not accepted. We have to find a different number, perhaps, or perhaps it doesn't exist, in Z75. And the answer is, well, some numbers will have an inverse and others won't. So in other words, we can, this is, remember, we call this the reciprocal, but it is, what it really is, it is the multiplicative inverse. Meaning that if you multiply 4 with its multiplicative inverse, 1/4, then the result is 1. So now we're looking for a number in Z75, if you multiply with 4, you get 1. So if we would know that, if we would have such a number, what we would do? Well, we would multiply both sides with that number, and then by the property that I just said, this number times 4 would just be 1. And then you have x equals, and that's the number that, whatever this 7 times whatever this extra number was, we're going to find it, don't worry. We get a solution. So the question is, how can we find the inverse of 4? It's not a reciprocal. So inverse is not a reciprocal. The reciprocals are for rational numbers. Reciprocal means 1 over, right? That is the official name of it. And so for us, before we worked in congruences, when we worked with regular equations and rational numbers, reciprocals were our inverses. But this is not the case in these guys, in these congruences, in the calculations modulo a certain number. Now, the issue, therefore, is, well, perhaps inverses don't always exist. Well, in fact, we know that inverses don't always exist because even in the rationals, 0 is the number, but it's the only number that has no inverse. In Z75, there are other numbers that have no inverse. For instance, let me give you a number. So not all numbers in Z75 have an inverse. Okay, and why is that? Well, suppose 5 had an inverse. Suppose A is the inverse of 5 in Z75. What does that mean? So inverse means that 5 times A is 1 in this ring, in this collection, so mod 75. 5A is equivalent to 1 mod 75. That is what it means to be an inverse. Okay? So I'm saying, suppose we have such an A. So I'm going to show you that it cannot be. It's basically proved by contradiction. All right. So let's multiply both sides by 15. Okay, and if you, this is a truth that is always, this is always true. If you have an equation, you can multiply both sides with the same quantity, and it doesn't change the equality. The equality stays true. So we can multiply both sides with 15. So I'll do this so I'm going to multiply here with 15, and here also with 15. Now, what is 5 times 15? 5 times 15 is 75. But 75 is not even a number in here, so we know that if we get numbers, remember how multiplication here goes. You take two numbers, you multiply them, but then if the number is beyond the range, you just reduce it modulo 75. You find the remainder modulo 75. You do the mod 75, right? So, what is the mod 75 of this? Well, remainder by division by 75 is actually 0. The remainder, right? Not the quotient. The remainder is 0. So mod 75. Right? That is what it is. So what we have found here. So this is 70 times 5 times 70 is 0 times A is 15 mod 75. But with 0 times A, what is that? 0 is always 0, right? So this is 0. So we find that 0 is equivalent to 1 times 15, which is just 15, mod 75. What does this mean? This means that 75 divides 15. Yeah, that's not the case. 75 doesn't divide 15. That is a contradiction. So this shows that it is impossible for 5 to have an inverse. That's bad news. Because if we have if instead of 4x we would have 5x, it might be something that we cannot solve. But there is a good news, is it's not true that there are very few inverses, because if you think about, now instead of working in Q, you could think, well, is it not like working in Z, the integers? And which are the inverses which numbers have an inverse in Z? Well, it's the numbers whose reciprocal is back in Z, and that's only 1 and minus 1. So in Z, the inverses are plus and minus 1. The numbers that have an inverse, the inverses, the invertible numbers, one says, are plus or minus 1. In Q is everything except for 0. So what's in 75? It's somewhere in between. It's not everything, but it's also not nothing. And the result is this in general. So this is the result or fact that we're going to use all the time. If A and M, the GCD of A and M is 1. We talked about GCDs last time. I mentioned it, but let me repeat this. This means that A and M are, we say this, and I'll put it in a different color, relatively, let me write it properly. Relatively prime. And remember, the name was somehow meaning that they don't have any common primes in their prime factorization. So this is the same as saying that the GCD is 1. If the GCD is 1, then A has an inverse modulo M. That means A, B, there's an inverse, let's call it B. A times B is equivalent to 1 modulo M. So it guarantees the existence of this B. So let's see, in our case, what's the GCD between 4 and 75? Well, we could do the algorithm, the Euclidean algorithm, but we can also very easily see this. We know the prime factorization. This is 2 squared, and this is what? 3 times 5 squared, right? If you see it, you're convinced, right? How you find it? Well, that's not so hard, right? And you see they have no primes in common. They are relatively prime. So this GCD is 1, right? Remember that, how did you do the GCDs? you look at of every prime, you look at the lowest power that occurs in both. Since don't have anything in common, it's all going to be power 0, so the whole thing is going to be 1, right? Okay, so this is true, so we know such a B exists. This fact is allowing us. But now is the question, how do you find it? Aha. And here is all the reason why I made you do this. So to find the inverse okay, how do you do this? I'm going to do it on the example, that helps perhaps better understand it. And the answer is the Euclidean algorithm that we discussed last time. And that's why I emphasize it's such an important algorithm. I'm going to make a quiz on it, because it's something that we use all the time. Let me explain how it works. So remember what you had to do. We had these two numbers. You took the biggest one and then divided the other by, you did a division algorithm on these two numbers. Now, how many times does 75 goes? Does 4 goes in 75? Okay. Well, that would be 72, 18. That is 72 plus 3, right? 24, no, what did I? Yeah, 72 plus, yeah, okay. Well, remember what we did? I'm gonna do the coloring that we used all the time. So we have, I forgot a little bit which coloring we used. So we took the number that we divide. So we have 75 and 4, right? And so these are the numbers that we used. When we normally, I said we circle them in, we'll see what I mean. So now we're going to take these two, the last two that we have here, so 4 and 3, and repeat the division. Well, 3 goes only once in there, and the remainder is 1. And we know once we have 1 that we have found the GCD. Now, remember, we said the GCD is 1, so that's verification of that claim, right? We see it again. Now, what did we do then? So that was the forward part. Now the backward part was to find the Bézout form. What was the Bézout form? Was writing 1 as a linear combination and a number of times 4 and another times 75. If you would add them up, you get 1. Of course, 1 is going to be a negative number, but we don't know yet exactly which one it is. How did we do this? Well, we started from the back, okay, and used this to write 1. This is all now, yes. So this is 1. We're going to write now 1 as, and I'm not going to color them anymore. I'm going to circle them. 4 circled minus 1 times, but let me not write that, 3 circled, right? So these are the circled numbers now. So instead of coloring, I'm just going to circle them. Okay, and then we combined if necessary, which don't have that. This takes care of this equation. We take the one above, just above it, use the remainder to rewrite it. This is the 3, so this 3 here, this 3 I will write now as 75 minus 18 times 4. So we get 4 minus, the whole thing, be careful, there's a minus in front of everything, so that is 75 circled minus 80 times 4. Are you with me? Okay, so where are we? So let's remember there's always 2 steps here, except for the first time perhaps, is to combine like terms, where like terms means circled ones. So we have a 4 here and we have a minus, so 18 4 here, so altogether 19 times 4. So 19 times circle 4 minus circle 75. And here is the linear combination that writes, so this is all 1, right? So here it is the Bézout form that we have. Let me rewrite it. 1 is 19 times 4 minus 75 circle. Now, what we are working for is, remember what we want to do is 4 times B is equivalent to 1 mod 75. This is what we're looking for, right? Remember, we set out to find the inverse of 4 modulo 75. So what does it mean to work modulo 75? That means you ignore all the multiples of 75. So this is a multiple of 75. It's minus 1 times. In general, it will be more. We'll do other examples. And therefore, we know that if we work mod 75, it's gone. And so only the first term remains. But look, I have what I wanted. The 4 is my circled number, and b is 19. So we see that 19 is the inverse of 4 modulo 75. Now, some people would like to write this like this, 4 inverse, but I don't think that's a good idea. The textbook doesn't do it. I don't like to do it either. Sometimes people do this because, yeah, it's confusing. You think of reciprocals all of a sudden and you start making mistakes. I have seen people, I've explained this 100 times, and then when they have to do it, they still come up with the reciprocals. So be very careful with that. So don't write that, don't use that notation. Okay, so remember that there was not the actual question. The actual question was solve this inequality, but we said, once we have an inverse for 4, we know what to do. We're going to multiply both sides with that inverse. So we have 4x. This is the equation that we're trying to solve, right? So what we now do is we take this inverse and multiply both sides with that inverse. So I'll do that so we do times 19 and we do times 19. Now, you can calculate what this is, 19 times 4. That's 19 times 4, but we know it's equivalent to 1 mod 75. That's the whole point. So let's not waste our time calculating something we know already. So this is 1 times x, which of course is just x. And what is this then? Well, 7 times 19. Now that I have to work out. So 19 times 7, that is 133 mod 75. But, okay, 133 is not within our range, so we have to reduce this mod 75. Here it is very simple. If you subtract 75 from it, you see that's 58. Remember, if the number you're trying to find is slightly bigger than your modulus, then you just subtract the modulus. That's what we do with clocks, right? If you say 17 hours from now, okay, maybe that is 12 hours from now, so 5 hours later than noon. Right? So something like that. That's how we calculate things, right? Okay, so this is how we solve linear congruence. So let me do another example where we have to do, let's do this here. Okay. So let's solve the following equation. 101 times x is equivalent to 2020 mod 4620. Now this seems, this is going to be difficult, but okay, let's just do it the way that we do. What do we need? So I repeat, what is necessary for us to be able to solve this is that this number in front of x can be inverted. We can multiply with something to make the whole thing 1, so it disappears. Of course, we have to multiply the same sign with the right side with the same number. So we are guaranteed to have that if this number is relatively prime with this number. Notice that this number is not relatively prime with this number. Is that an issue? Not at all. Right? Because in fact this could even be 0, or this could be even whatever you want. It really, these numbers can be whatever you want, the way that they relate to each other. It's this one and this one. Now that will come out anyway if we try to solve this, because step 1 would be to calculate the GCD of 4620 and 101, so verifying that it is 1, but this calculation is not for nothing, because we will use it to find the inverse. So we do this using the Euclidean algorithm that we have described last time. Okay, let's move on. Let's do this. 4620, how many times does 101 go in there? Okay, I'm not going to do it in my head. It's probably 46 times, but let's just see. No, it's probably 45 times. So 4620 divided by 101, yeah, 45 point something, so 45 times. So I'm going to now only circle these numbers, right? And then the remainder, what is that? 45 times 101, this number is 45, 45. So what are we missing? Is 55, 75. Right? I want to make sure that I don't make mistakes here. 4, 6, 20 minus 45, 45. That is 75. Okay, so that's 75. This we don't need anymore. And we repeat the process with the next numbers, 101 and 75. Now that goes there only once. And what else we have? 26, right? Yeah, 26. Okay, how many times is 26? Sorry, now we do, no, that's, so we have 75 is 26. How many times does 26 goes in there? Not 3 times, so 2 times. So this would be 52, and then what is missing is 23. Okay. Keep going. 26 and 23. Well, it goes in there once, and the remainder is 3. Right, there's a 1 here if you want. Okay, so now we do 23 and 3. If you don't understand what I'm doing, go look at the video on GCDs and also the review video for the quiz on GCDs. This goes in there 7 times, that's 21 plus 2. So now we do 3 and 2, that goes in there once, and remainder 1. So this is our GCD, is 1, as we expected it, or we were hoping it to be. And now we have to go backwards. So 1 is equal to 3 minus 2. Okay, then we use, so this is now taken care of. So now this one, we use this 2 here by rewriting it. So this 2 will now be written as 23 minus 7 times 3. Remember, what I do is bring this to the other side, and this gives me a new formula for 2. And then I combine these two like terms, the 3's, there's a minus minus, so I have 8 times 3 minus 23. 8 times, right? Because sorry about this, a little bit more careful. Because we have a minus minus is plus 7, and we have also, so we have a plus 7 here and a plus 1 here, so altogether plus 8. Okay. Next, that means we have done, we used this formula, so we move to this one. And we rewrite now 3. So 8 times 3 can be written as 26 circled minus 23 circled, and 8 times that minus 23 circled. We combine there's only 126 appearing there, so but we have a minus 8 times 23 in the first and a minus 1 in the second, so altogether minus 923. Okay, so now we use this one to rewrite the second, the 23, the second number, the smallest of the two circled numbers. That is 8 times 26 minus 9 times, and that would be 75 minus 2 times 26. Okay, I'm just using this, I'll bring this to the other side and rewrite 33, and now combine these two terms. Minus 9 times 2, that is 18, plus 8 is 26. So I get 26 times 26, see, that's how it gets confusing, right, if you don't circle things. And now we just, the circled numbers have nothing to do with the numbers outside. We pretend that these numbers, you notice that we don't do any calculations with the circled numbers, right? They are for us kind of like, yeah, protected by the circle. We don't do anything with that. Good. Well, now we're going to replace which of the 26? The circled one, right? Okay, because that's the circled one. Okay, so this is 26 times 101 minus 75 circled, and then we also have another minus 975. So if I combine this, it's 26 times 101, and then I have a minus 26 minus 9, right? 26 times minus 1 is minus 26, and minus 9, that is minus 35, 75. Okie dokie. And there's one more left, and then we're almost done. And just for clarity, I'm going to write it here. So we have 26, 101, minus 35, and now here is the replace 75 by 4,620 circled, minus 45 times 101 circled, and I combine the 101s. That is, we have a 26 there. Oh, that you see these numbers can get big, right? So we get 35 times 45, well, minus minus, so this plus, that's 1575, plus another 26. So if I combine the coefficients of 101, then it's 1601, 101, minus 35 times 4620. Okay. Step 2. What do we do now? Why would we? So remember, this is just what 1 is. This is just a form of 1. You can verify it, but let's trust ourselves that we did it right, especially because I'm actually also looking at what the book says, and it's exactly the same answer that I have. What do we do with this thing? Now remember, what are we working? We're working modulo 4620. That means that any multiple of 4620, this is a multiple of 4620. And you see, it's a real multiple. Huh? It's juicy, meaty multiple here, but we can ignore it. So if we do this mod 4620, only the first one remains. So this is our inverse of 101. So now we have found the inverse. So the inverse is, I'll write it again, 1601. Notice that it is smaller than 4620. It's an element. Remember, this should always be elements in the set of remainders, right? And that's okay. That is correct. And so what we do now? Well, step 2 is we take our original equation, which was this one, 101x times 2 is equal, 101x equals 2020 mod 4620, I just copy it. We multiply both sides with this inverse, 1601. So 1601 times this and 1601 times that. Now, the first one I'm not going to calculate because I know the answer. What is the answer? 1, right? Because that's the whole purpose. That is exactly what I've been doing here. This is 1. So this whole thing is just 1. So we just get x here. Now, the other one, I have to work it out. So that is 1601. Sorry, it's a bit weird written 1601, but that's what it is, right? Times 2020. That is, okay, I'll write this out for you, is 234,020. That's an answer, but not a good answer because we need mod 4620. Okay, that's we're going to do that. How do we do that? Well, divide this number by 4620. Divide by 4620. And I get 700 and a bit. So this is 700 times 4620. And how much am I missing? Very little, I think. So 700 times 4620, that is actually 3. This number is 3234,000. So what am I missing? Only 20 plus 20, right? You see the difference in the two numbers? Okay, so I can erase this. And so I find that x is equivalent to 20 mod 4620. Okay, now I admit now I realize that I actually gave a number where you say, okay, but I kind of knew that, Professor, because 2020 divided by 101, even in the regular numbers, is 20. Sure, but I just wanted to show you this is what you get if you use the method. Okay, and in general, of course, we cannot do this division, and it's not allowed. We're not allowed to do this division. So the only way we can solve this is this way. Okay. Okay. Right. Okay. So I'm going to leave a couple of homework problems for you and do this. But I want to go now to another problem on congruences. It's a famous problem. It has actually a name. It's called the Chinese remainder theorem. It's a bit weird name, wild Chinese, right? I mean, remainder, okay, remainder, we have seen remainders, but what Chinese? Well, I don't know. People at some point give names to things, and I find it a little bit disrespectful in the sense that, well, this was a problem that was studied by the Chinese, but also by the Indians, so it's kind of not really correct to just attribute it to Chinese, but we find it in a book of a mathematician in the 1st century. So this is in the 1st century AD. This means almost 2,000 years ago, and then his name was Sun Tzu. I'm sorry, I have no idea how to pronounce Chinese, so I try my best. And he wrote the following. I'm going to read the quote, it's also in the textbook. There are certain things whose number is unknown. So it's kind of saying, what is x here, right? Okay, and so. When divided by 3, the remainder is 2. When divided by 5, the remainder is 3. And when divided by 7, the remainder is 2. What will be the number of things? Okay, so let's first write down what he's asking. So there are certain things whose number is unknown. Okay, at the time of writing, they didn't use variables yet. They didn't know the x yet. That is something that I told you was from the Persian Islamic mathematicians like Al-Khwarizmi who came up with these things. So, but for us, we know now, he's asking x. Okay, what is x? That's what he's asking. And what he says, when divided by 3, the remainder is 2. Well, we have exactly a way to say that. Divide by 3 means mod 3. So it says x is equivalent mod 3. What is the remainder? 2. This is exactly writing in our notation the fact that if you divide x by 3, the remainder is 2. When divided by 5, the remainder is 3. You agree that this is what this means? Okay, and then finally, when divided by 7, so now this is about the remainder is 2. Is this mod 2 or mod 7? When divided by 7, so we're doing the mod 7 part, the remainder is 2. So find an x that satisfies all these 3 numbers. Now, you could try to do trial and error and find these. First of all, perhaps you might question that there is such an x. And in this case, I think the answer is rather small, that you could perhaps at some point arrive at by just trial and error. Okay? There is a different method, and this is called the backtrack method. I'm not going to discuss it, but it is in the book. Back substitution method. It's actually much quicker in this case. But I want you to know the actual algorithm, because again, this is something that we will use later in our cryptography, where we need to use this for much. Although we always look, we use very small numbers, but in reality, when these things are used, we're talking about not 1-digit numbers, but 10-digit numbers. And back substitution is horrible at that. Well, in fact, it would not really work. The numbers get too big. So this is the question of that Sun Tzu, or this Chinese remainder theorem problems. And so people would make a lot of problems, right? It's easy to make a problem like that. In fact, I'm going to make quizzes like that, so you're going to find. But it's not easy to answer. I mean, especially if you don't know of any good method. So we don't know what methods these people had. So the solution I'm going to present is not necessarily the solution that they had at that time, because at least not in the terminology that we will use. So first of all, we have to kind of discuss a little bit, how do we are guaranteed that we have a solution? And the one condition that we need is that these moduli, these 3 moduli, have to be, I'm going to write this, pairwise relatively prime. Pairwise, I mean any 2 are relatively prime, any 2 have GCD 1. But a better way of formulating that is that if you look at the prime decomposition of all these moduli, and there don't have to be only 3, there could be 5, there could be 2, and so we will discuss how you deal with the general case. Okay, so in general we have moduli. The moduli the plural of modulus is moduli. That's a Latin plural that we use. Moduli are in general M1, M2, all the way up to Mn. You know, I'm going to write Mk here. So there could be k moduli, in this case 3 moduli, and what we need is that they have to be relatively prime, pairwise relatively prime, which means, it's easier to say it that way perhaps, or easier to grasp or see, is that if you take the prime factorization of each of these numbers, no prime occurs in more than one spot. Some primes might never occur, of course most primes will never occur, but if there's a prime, it can only be in one of those, then they are relatively prime. Okay, now 3, 5, and 7 themselves are prime, so yes, they are different primes, so this is definitely something that satisfies this condition. And so instead of just 3 conditions, we have now condition x is equivalent to something mod m1, and all the way up to x is equivalent to something mod the last one, mk. Now what is this something? Okay, let's give it a name, a1 all the way up to ak. And what are these numbers? Well, they're just numbers, doesn't matter what they are actually. They can be arbitrary integers, okay? So what this now says is, the theorem says if you have this relatively prime, then you can find a solution to this equation that simultaneously. So you can think of this of a system of equations that you try to solve simultaneously, right? Now notice that if x is 2 and x is 3 and x is 2 without the moduli, this is obviously that's a system that's never going to solve, right? And we have seen normally, if you want a system to be a linear system to be solvable, you need basically as many equations as there are variables. But here there's only one variable and many equations. That's kind of strange, right? But we'll see. It has solutions. There's such a solution. There's even a smallest one that you can find. Namely, the smallest one. So there is a unique solution, positive solution, x less than or equal to the product of these moduli. So you take the product of all of them, and I'm going to call this little m. Yes, so you take the product of all this. So what is m here? 3 times 5 times 7. 15 times 7, that's 75. No, that's not 75. It's 105. Sorry, what was I saying here? People. 105, right? M is 105 in our case. We will solve this. I'm going to get myself a little bit of space here. But I'm going to first discuss a little bit how do we set it up in general. But I will work it out on the example. So step 1. So we have, I'll write it again. We calculate this number, m1 times m2, all the way up to mk. But we need some other numbers as well. This is capital Mk, and it is m divided by mk. Now what does that mean if you think about it? Little m is a product of all the moduli, and what am I doing now? I'm dividing one of them away. Oh, sorry, mk, sorry, I meant here in general, I went to use a different index here. Sorry. So mi is m divided by mi. So for each I, for I1, 2, 3, all the way up to k. So yeah, what is k here? Perhaps here in our example, k is 3, right? There are 3 equations, 3 moduli, and the product is 1 to 5. So what are these numbers? So what is m1? So okay, this will be little m1, this will be little m2, and this will be little m3. So what is big m1? So big m1 is a product of all the moduli except for the ith one, right? Because it's all of them, that's little m, and then you divide away the ith one. So m1 is the product of all the others. That's what you have to say. So this is 5 times 7, this is 35. What is m2? It's the product of the 2 other ones, 3 times 7, that's 21. And finally, what is m3? m3 is 3 times 5, 15. 3 times 5, that is 15. Now, by virtue of this choice, the GCD of mi and capital Mi is 1. Right? Why is that? Well, I just divided away. And we know that there are no other primes. So there are some primes in mi that are not in the others. And if these guys are the others, and this is mi. So there are no primes in common, so this is GCD is 1. So in particular, this means that we have an inverse. This means that mi has an inverse mod little mi. Capital Mi is an inverse mod little mi. So it has an inverse, and let's call that inverse yi. So what does this mean? I'll write it out, i.e. this means that if you do yi times capital Mi, you get 1 mod little mi. You still following with me? Well, that's perhaps already step 2, I should call this step 2 here. Well, step 2 is finding this one, so this is step 2. You'll see, this is a calculation. Remember, how do you calculate the inverse modulo? We saw it upstairs here, right? This is how you do it. Oh my God, a lot of calculations are coming. Okay, now finally, so step 3. Oh, what is that for? What did I do? Step 3. I'm gonna give you a proposing the solution, and the solution is A1 capital M1 Y1 plus dot 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 plus AK capital MK YK. And that's going to be the solution. Now the solution, yes, okay, let me say that, and we will see later what we do, how we do that. So what we need to calculate is, well, we have the M1s, so now is the question, what is Y1, what is Y2, and what is Y3? Well, do we also know what the A's are? Yes, this is A1, this is A2, and this is A3. So it's very important that when you study this algorithm, and I'm going to ask you to do it in a quiz, that you know what is what. Because there's a lot of numbers now, and you have to declare each of these numbers and work with them. Okay, the A's are the ones that are on the right-hand side. Okay, these are the AI's. The MI's are the moduli. Okay, then the capital MI's are the product of the remaining moduli. The YI's going to be the inverses modulo. So we have to, what is this? Y1 is going to be the inverse of 35 modulo 3. So okay, let's work this out perhaps a little bit here. Sorry, and let me make this a bit smaller because it's from another test. Okay. So what is Y1? So remember how do we solve Y1? I'm going to put it up here. Y1 times M1 should be equivalent to 1 mod little m1. So what does it all mean? Y1, we don't know yet. Capital M1 is 35, should be equivalent to 1 mod 3. Well, 35 mod 3 is actually, I can reduce that already, right? So notice that this number is already too big, so to speak. So the first thing I should do is reduce it modulo 3. What is it then? That's 33 plus 2, so this is actually 2, right? So this 2y1 is equivalent to 1 mod 3. So what can I multiply this with to get 1? Now we have to find the inverse of 2. But there were very few numbers to try, right? 0, 1, and 2 mod 3. So these are just small numbers that we don't have to do this gruesome calculation, although in general one needs to, but for this small problem we don't know, we can do it in our head. If I multiply both sides with 0, if I multiply 2 with 0, of course that's never going to work. If I multiply 2 with 1, of course that's never going to work. So there's only one choice, 2. So multiply both sides with 2, right? So if I multiply here both sides with 2, so multiply with 2 here and multiply with 2 here. 2 times 2 is 4, which is the same as 1 mod 3. So we do get indeed that y1 is equivalent to 2 mod 3, right? This is just rewriting this here. Let's solve the other one. I'm going to keep doing this here. Let's get a little bit rid of some su. So we have to now solve y2 m2 is equivalent to 1 mod little m2. What is everything? y2 we don't know yet. Capital M2 is 21. Has to be equivalent mod, and our modulus is now 5. Oh, but 21 mod 5 is what? Is 1, right? Oh, there's nothing to do. y2 is equivalent to 1 mod 5. So we're there. We know what it is. Okay. And then finally, y3 m3 has to be equivalent to 1 mod m3. So y3, which we don't know yet, m3, capital M3 was 15, should be equivalent to 1 mod 7. Oh, this is again easy because 50 mod 7 is 1. So we see really the y3 has to be equivalent to 1 mod 7. Okay. Now what this means is we're going to take y1 to be equal to 2, y2 equal 1, and then 3 1. Okay. So now finally we have everything. All the things we need, we have to put it together in this fashion. So let's see what this means here. So x, let me give a little space here. X is, I'll write it up, a1, capital M1, little y1, plus a2, capital M2, y2, plus a3, capital M3, y3. Okay, so what is that? I can get rid of this line here. A1, what is A1? Remember, these are these guys on the right-hand side here. So that is 2. M1, capital M1 was 35, and little I1 was 2. Y1 was 2, plus A2, 3, capital M2, 21, Y2, 1. So the Y's, remember, are these numbers right now, right? Okay, I know they are modulo, but we just take the number themselves. Okay, plus A3 was 2, capital M3 was 15, and little y3 was 1. Okay, so this is the number we look for. That is 2 times 2, that's 4, times 35, 120, 140, plus 63, plus 30. And so altogether, this is 200, wait, I feel like I made a little mistake here. 233? No, 233, yeah, 233. Now, is that a solution? Now, remember, in the theorem, where is it? It says there's going to be a solution modulo, it is a Chinook solution less than m. How do we find this? So we have to do one more operation here, and perhaps it's better to do this in here. So we have to take mod little m. So that's the last. Sorry, mod m. That is actually the actual solution. So let me box it that way. So this is how what we do. So we take this combination and then have to still do one more step. So perhaps step 3, step 4, I don't know what to call it, is reducing this mod. Where's where's here? So here we have to do this. This we have to do mod. So we have to calculate this number. Sorry. So we have to calculate this number as mod. And remember what was our little m? We have it written down here. It's 105, right? Mod 105. And what is that? Well, 105, okay, we have to find 233 mod 105. Well, 233, sorry, I'm going to make myself a bit space here. So what is that? 233, that is 2 times 105, that gives me 210, and then 23 left. So this is equivalent to 23 mod 105. Or rather, perhaps, well, it's a number. I don't want to write it in it. So it is 23. Okay? So the answer is 23. And you can now check that the answer is correct. 23 minus 2, that is 21, is indeed divisible by 3. 23 minus 3 is 20, divisible by 5. 23 minus 2, that is 21, divisible by 7. That's what this means, right? Okay. So that is how we solve the Chinese remainder theorem. I'm going to do one example still. Again, I cannot do really two big numbers, otherwise it will take us forever. But so let's look at this one. X equivalent to 1 mod 5, x equivalent to 2 mod 6, and x equivalent to 3 mod 7. So first of all, what is little m? Is 5 times 6 times 7. That is 30 is 210. Okay. The numbers are relatively prime. This is a prime. These two are prime numbers, and this is 2 times 3. So no prime number in they have in common. So what is A1? So I'm going to write the A1s just here, right? This is A1, 2 is that's A2, 3 is A3, this is M3, this is M1, this is M2, and this is M3. Okay, we have everything. Well, no, we need the capital M's. What are the capital M's? So I do this perhaps in a different color. What are the capital M? Capital M1 is the product of the remaining two. That's 42. Capital M2 is the product of the remaining two. So everything except for the second one. That is 5 times 7. So if there would be more than that, I will do an example perhaps in the homeworks with 4 or 5 even. So that's 5 times 7, and M3, that is 5 times 6, that is 30. Okay. So now what we have to find is Y1 M1 should be equivalent to 1 mod M1. Or in general, let me write it just for, this is the equation that we have to solve for each of the i's. So if I is 1, what is this then? I go back to black here. So in the case I equals 1, then the equation becomes Y1 42 should be equivalent to 1 mod 5. But 42 is the same as 2, so 2 times Y1 is equivalent to 1 mod 5. Now mod 5, so mod 5, there's only 0, 1, 2, 3, and 4. And try a little bit. 2 times 2 is 4. No, that's not 1. 2 times 3 is 6. Ah, that is 1. So if I multiply both sides here with 3, which is the inverse, but I don't need to calculate it really, just by trial and error I see here. Multiply both sides with 3, right? Then you come 6. This becomes just 1, y1, and this is 3. So y1 is equivalent to 3 mod 5. Okay, so we find that y1 is 3. Okay, so what about I equals 2? So now we have to solve y2, m2 is 35, and you have to do this mod 6. Now 35 mod 6 is 5. Sorry, this has to be equivalent to 1. Sorry, I forgot to write the equivalent to 1 here. You see, you might ask, why do you write 35 in the back? Well, you can do that, right? I know you normally write a number in front of the variable, but there's no reason to do that. I'm just following. I don't know. I just follow this pattern, right? Okay, so 35 is the same as 5 mod 6. So this, I write it now in front. 5 times y2 mod 6. So what's the inverse here? Now 6, again, is only 0, 1, 2, 3, 4, and 5. 0 and 1 we know is never going to be inverses. So 2 times 5, 10. No. 3 times 5 is 15. No. 4 times 5, 20. No. 5 times 5, 25. 5 times 5 is 25, which is equivalent to 1, right? 5 times 5 is 25, which is equivalent to 1 mod 6. So if I multiply both sides with 5, I get 1 on the one side, and what do you get here? 5, of course. So this is solving it for this I is 2, and then finally for I is 3. What do we get here? We need to know now y3 times 30, and we have to calculate this is equivalent to 1. There's always 1 here, right? Be careful. Don't go look at these numbers yet. We're not doing this. We're working. This is a different calculation. We are not calculating this yet. We're calculating this. So this is always 1 here. It's a very common mistake that people start putting these numbers in here. No, that comes all the way in the end. The a's are only used in the last step. Okay, so this has to be modulo 7. Now 30 modulo 7, that is 2, right? Because that's 28 plus 2, right? So this 2 times y3 equivalent to 1 mod 7. And do you see the inverse of 2 mod 7? Again, trial and error. 4, right? Okay, right. If we multiply both sides with 4, so we multiply with 4 here with 4 there, then 4 times 2, that's 8, which is 1. So we get y3 is equivalent to 4 mod 7. So we find our y1 is 3, y2 is 5, and y3 is 4. Remember, we take the numbers that remain as themselves in the formula, and that the formula is x is a1 m1 y1 plus a2 m2 y2 plus a3 m3 y3. And all this has to be calculated. Well, perhaps better to say it here. We take the remainder of division modulo little m, which was 210. Okay, because this number normally is way bigger than that, than this 210. So we have to still do one more step there. Okay. Good. Well, what is the ace? Well, the ace, remember, now we're going to use these guys. This is the only, at this stage we use this. That the first one was 1, capital M1 was 42, and little y, and y1 was 3, plus A2 was 2, capital M2 is 35. This is just putting numbers, right? This is something you can give to your nephew, if he wants a little nephew that is sitting next to you and says, oh, can I do it, can I do it? Okay. A3 is 3, capital M3 is, where is capital M3? 30, and Y3 is 4. Okay, so this is 126 plus 350 plus 90 times 4, that is 360. So if I'm still fresh enough to do this in my head, that is 11, 13, and 7, 8. 836. Now we have to work this mod 210. So, okay, what is 836? 836 divided by 210, that is 3 times. So that is 836 is 3 times 210. And what is left then? 3 times 210 and minus, that is 206. That's the remainder. Right, it is less than 210. I was a little bit worried, looked like almost, because, but it is, okay, it is a remainder of 210, right? So we find the answer is 206. And you see here, this particular problem, x mod 1, the numbers are still relatively small, but if you would have to guess this number, it would take you quite a lot to find that number, right? Okay, there's more in this chapter, but I'm going to stop here and I'll do this in the next session. I think I want you to concentrate on these two things, finding inverses and being able to do the Chinese remainder theorem. I'll do homeworks on that, and there will be quizzes. Be forewarned, there will be quizzes on this too, because again, this is things that we're going to need use in our cryptography. Okay, I'm going to prepare you so that you can set up your cryptographic system once you're finished this course. All right, so see you in the next